It is my pleasure to introduce our last but not least keynote speaker, Marc Rysman. Marc is a professor of economics at Boston University. He has been one of the main contributors to the field of empirical I/O over the last 20 years. His work on two-sided markets and competition in industries with network effects is seminal and has received thousands of citations. His work on dynamic demand of durable products with Gautam Gaurisankaran has become a staple in empirical I/O, and it's very commonly used and is often referred to as the BLP, dynamic BLP model. More generally, Marc has worked on a broad range of important topics in empirical I/O and many important industries as well. And he has been a generous contributor to the profession, being editor of the Rand Journal of Economics and associate editor of multiple journals, and supervising a large number of fantastic PhD students. Today he's going to talk about his more recent work on a fascinating industry, the Subsea Internet Cable Network. Please join me to welcome Marc.
All right, thank you so much. Victor's thing is working, so okay. Victor, thank you so much for that extremely kind introduction. Thanks so much for including me on the conference. I really enjoyed my time here, and yeah, there's so much to learn about dynamic estimation and econometrics, but it's really helpful to be here. Yeah, I'm delighted to have a little while to talk about this paper. I understand we have like kind of a deadline to get out of the room at 5 after or something. 6:05. So anyway, I'm happy to take questions as we go along. I know that the industry is not something that everyone has heard about, so please ask any questions. And our model is pretty involved, as you'll see. I brought a lot of slides, but you know, we'll keep it moving. And this is one of my junior colleague at BU, Gian. We got involved in this, interested in subsea internet cable, so I'm excited to tell you all about it. So we're going to study fiber optic cables that are underneath the water and that they kind of connect. Basically, if you're communicating in any way across the ocean, like almost surely it's going over these fiber optic cables. Some people think like satellites are important. Satellites are just tiny, maybe someday, but for now they're just like a total non-issue. They're just a tiny, tiny fraction of what's out there. It's all going over. You know, wires are better than satellites. Massive growth, as you can imagine. And then we have these kind of punchy quotes about this is, you know, that the single most important factor in the growth and success of the internet. And this great quote from this woman at Google: people think that it's in the cloud, but it's not. It's in the ocean. So, you know, it's really linked to, you know, we'll talk about it a little bit. We're going to just focus on cables, but it's really linked to the build out of data centers, and that's something I think a lot of people have been hearing about through all the kind of investments in AI. And so we're going to focus on two inefficiencies in the market. One is the kind of network nature of the product. So that when you build a cable here, it's going to affect global flows of communication. And you can imagine investors in the cable might not be internalizing all that when they make their decisions. And the second one will be business dealing. So we'll see that there's like a lot of building, let's say in North America to Europe route, almost no construction at all in the South America to Africa route. And part of the story might be something about business dealing. Are they, you know, are those investors that are kind of going to North America and Europe, are they you know, kind of ignoring perhaps larger social gains in these underbuilt routes to kind of steal market share from all of the existing capacity in these more built up routes? That's one of our big questions. So our kind of research questions today will be: how much does cable construction contribute to the growth of usage? How does private investment in cables deviate from the social optimum, and kind of what factors, particularly between these two, are determining that outcome? So we're going to present a new data set on undersea cables. We're going to develop a structural model of these international data flows. We're going to have sort of country to country demand to exchange data that's going to look sort of like a gravity equation type model, but then it can't just go straight from country to country. It's got to go over these cables and we'll have a model of how data moves around these cables, and then we'll have this previous stage where we have the firms that build cables choose where to build their cables, and we'll try to kind of internalize that. It's mostly going to be a static model, but we do have this kind of part I've actually never presented before on dynamics, where we're trying to make it a dynamic model. But of course, this seems like the audience to try it on, so I'll try to spend a slide or two on how to think about it with dynamics. It's really complicated, but what we do is really simple. If we did it right, it would be really complicated. And then we're going to use our results to kind of particularly contrast this private and social cable construction. I guess I'll kind of skip the literature review, just because we don't have that much time, but there's many interesting papers. Not too much. The closest one, I guess, is this one, which is actually studying kind of the same data set, but not really focusing on networks, but kind of their focus is somewhere else. And so one thing, I have this slightly defensive slide of citations. So one thing we're going to see is that distance is going to be really important. I think many people think, how could distance matter on the internet? Like, data basically moves out through these cables at like half the speed of light. So how could distance be important? I just want to say, like, for people in this industry, distance matters. Like, sometimes these issues of latency and kind of real-time communication turn out to be really important. And so I just cited about these are all computer science papers kind of studying latency and distance, and these are more economicsy papers studying distance. But I'm just going to put that aside. But I'm happy to talk further about it as we go along. So here, kind of, this is this slide is probably not very helpful in understanding our paper, but it's good for understanding the industry. So this is an actual cable. These are the fiber optic wires that are like the size of a human hair. That's what everyone always says. And then it's kind of surrounded by steel, and copper delivers power and insulation and more steel, and that's supposed to kind of protect it under the water. You can see how big it is with someone holding it in their hands. Then you kind of roll it around. This is like you put it on a ship, and these guys, you can see there's like 5 grown men standing here, and they have room for like a lot more. But basically, they're trying to like push it down with their weight that helps it kind of like roll up properly. And then this is like an actual boat that's taking out here, and this cylinder is that cylinder, and they're going to string the cable out into the ocean. And then somehow G and I love this one. This is the plow. When you come close to the shore, a big problem is like anchors and stuff breaking these cables. And so when you come within a few miles of the shore, you try to bury the cable under the ground, and this thing would it's like 40 feet long. So to give you a sense of the size of it. And then here's an actual cable like coming out of the ocean and coming up into some landing station, which will then distribute it to some nearby data centers. And so just a little bit about the industry. You can think of like there's kind of a cable layer, and then there's an internet backbone, like level 3, which is now called Lumen. It was like a big player in the United States, and they would be kind of contracting with the cable companies, and then they're selling their services to the kind of last mile. This is kind of U.S. companies, Verizon, AT&T, and Comcast. They're kind of the last mile. And so we're focusing on this blue layer today. So we're not going to be talking all about this layer, but that's kind of where they fit in. Of course, there's some vertical integration. AT&T is in the backbone and in the cable market. And in some countries, there's a national telecom provider who's basically kind of doing all 3 of these. But that's kind of, we're just focused on the blue layer there. And just one last slide on the industry. One thing that's been really fascinating for this industry, it used to be all telecom providers that were kind of the owners. AT&T, China Telecom, Tata is a big player. But the last 10 years, it's been content providers integrating into the industry. So Google, Microsoft, Amazon, and Meta are all building their own cables loosely. Basically, they want the cable to go from their data center to their data center. That's and they want a lot of capacity, more capacity than AT&T's ever put in before. And so that's just a really highly specialized thing for AT&T or Tata to get out and do. And so they're just kind of integrating into the market and doing it themselves. And the implications of that, I think, are really, really profound for what's going to happen in the internet. Well, a little bit of a take on how they're different and how to think about that, but that's something we want to explore more in the future. Another thing to keep in mind, the level of economic regulation in this market is super low. And I think that's really surprising to a lot of the people that I present this paper to, but there's no connectivity regulation, there's no regulation about interconnection or pricing, there's just nothing like that. And so there is a lot of geopolitical interest in this market, but it's really about security issues. And the FCC has the right to kind of every cable that wants to land in the United States, the FCC has to approve it, but so it's through the FCC, but it's basically left up to these kind of homeland security type questions. And so it's just about security. So we're really not going to model government regulation at all. We're think of that as kind of there's some non-economic regulation, but we're not going to focus on it. So here's our data set. We have this company, Telegeography, that kind of has a lot of expertise in telecom in general, particularly in marine cables. We have annual data from 2002 to 2020, and then we're going to observe features of the cable, and you could think of these as kind of the explanatory variables, particularly potential capacity and length. Those are going to be our big explanatory variables. And then for the investment part, we're going to observe who the owners are and their construction costs. Then our dependent variable is going to be what's called bandwidth usage, and this is the cables sell to their customers, which are like local carriers or internet backbone companies, and then selling them bandwidth. They don't sell, they sell them part of their cable. You get like a chunk of their cable for yourself, and that's called bandwidth usage. And Telegeography keeps track of both total capacity and then how much is sold to the customer. That's going to be our dependent variable, and that's kind of the dependent variable that like the other papers in this area are using. We see it at the region pair level, bandwidth usage at the region pair level. So like in a region, I'll talk a little bit more about it, but it's loosely continents. You can sort of think of it as continents. So for instance, we'll see how much bandwidth usage is being sold between North America, or consumed between North America and Europe, or North America and South America. And so we're going to have to kind of aggregate everything up to that level, because that's like the thing we're predicting.
Just to understand, means we are actually using, or that you have access to, and you can choose not to use?
Yeah, it's a good question. So the you buy kind of space on the pipe. So you get a chunk of the pipe. You're a carrier, you're the local carrier. You get space on the pipe, and then you run traffic over that. And so what we don't see is traffic. Maybe that's like what you'd like. I'm just gonna interpret your question. You wish I saw traffic. Maybe that's the way. But traffic would be kind of maybe even better. Traffic, of course, varies a lot. We only have annual data. Just keep in mind they have engineers that are just devoted to managing the relationship between this kind of bandwidth usage and traffic, because it's costly. And so you could think of it as like a proxy for traffic. Okay. And then I mentioned there's going to be like a kind of gravity equation part of the paper as well. So some data issues to keep in mind. We're going to see this kind of usage. Well, we're going to think of it as usage between two regions, but we don't see the endpoints of that. So we'll see how much goes between North America and Europe, but it might have started or ended elsewhere. And so we're going to have to kind of have a model that deals with that when we try to predict usage. That's the second point. The first point up here is that we observe the kind of region pair at the capacity level, so we'll be kind of aggregating up to that level. And then we don't observe anything about terrestrial cables. So we've never been able to find a good data set on terrestrial cables, only these undersea cables. So we're going to just sort of imagine within a region with a continent, everybody has access to the same. That the network is sort of just as good everywhere. There's no, like, the US doesn't have a better network than Canada or something like that. So just kind of loosely, this is the data we get. We see all the cables, all the landing points. This is kind of the picture of the cables. but we're going to act because our dependent variable is only at the region level. We're going to kind of aggregate it up to these kind of region to region communication. So we sum up capacity across all the landing points into regions, and then we're going to think of paths. You'll see as I'll talk more about this, but we'll think of different paths that South America can communicate to Europe through this path or through this path or through a direct path. And so that's going to be kind of where we're headed. And you can see if I only have 7 regions, that's my dependent variable. I don't have that many observations. So that's 21 markets, and I have 19 years, so I have 309. So I guess here's what I want to say. Some people think economics now is all about having like massive data sets and doing machine learning. You can walk out now if that's what you're here for, because I don't have that. I have very few observations and a lot of modeling to kind of get something out of it. That's the plan today. We do a little bit extra with islands. I'll try to mention that. We have many country pairs, but that's just gets added up as kind of into these explanatory variables. The dependent variable, we have relatively few for modeling. And then there's going to be on the investment side, it's only 102 cables. Like we only focus on there's like 500 cables out there, but we only look at the ones that go between these regions. Most of the cables are really tiny. They go from Denmark to Sweden, or there's like Indonesia has the most cables in the world. They're all connecting all these little islands, but those cables wasn't what we're studying. We're studying, the big interregional cables. So it's only 102 cables, which is like 75% of the length of cable in the world. So we're getting anyway. It's not that many observations we have, so we have to do a lot of modeling to get there. Okay, so some definitions. We have countries, regions, and markets, and paths. Those are our 4 things that we're thinking about. So countries are parts of regions. Every country is part of one region. Regions are going to be a group of countries such that regions are basically defined that every country in a region can get to each other by a terrestrial cable, and anything between 2 regions has to go in the water. It has to be. So we know region to region communication is going to be through the data that we see, through the cables where we have some data. We have 7 regions. And so, we grouped Europe and Middle East into one region because they have a lot of terrestrial connection to them. Then markets are pairs of regions. So between a region is the market. And then paths are sets of markets that connect into regions. So there's like a direct path between Europe and North America, but there's indirect paths as well. Europe to East Asia to North America, Europe to South America to North America. There's going to be different paths, and I'll come back to this point. So let's start with the choices of the firms. We're going to start in stage 1, and then I'll tell you about stage. It's really, you can think of it as just one stage. There's just firms making these choices of where to invest, and then demand is realized. Okay, so firms just make a binary choice. They're just going to make a binary choice whether or not to invest in every market simultaneously. Okay, and then once they're made their investment choices, there'll be new capacity that results from that. And then there's going to be country to country quantity is then going to traverse the cable network, and firms profit from how much quantity ends up on the part of the network that they own. And then critically, investment in one market is going to affect kind of worldwide traffic flow. So here's the notation around this. M markets, J firms simultaneously make this binary choice, AJMT. So every period they're making a choice. So some like vector notation and for the whole world, this is capital A, the choices. Okay, and then they're going to think of the firms are going to know, they know exogenously how their choices lead to changes in capacity. So they kind of take as exogenous every period how much capacity gets built when we all make our choices. So this K tilde is like kind of the resulting added capacity that comes from a vector of choices in this market. It's a known deterministic function, and it's going to apply a cost. So there's going to be capacity, then there's going to be a cost. And if multiple, so one feature of this data is it's almost always we see multiple firms building together. Like there's these consortiums of firms building, and we've got just a super simple model of how these consortiums happen. If more than one firm chooses to build, they just automatically become a consortium. So if two firms choose to build in the same market, then they become a consortium, and then they split the capacity and the cost evenly. So we've got a pretty simplistic model. It's not something like there's no like efficiencies to joint building or anything like that. We kind of don't observe that much about like the bargaining process, so we didn't do that much with that here. Okay, but if you're this is kind of a big K is the total that's built in the market. Little k is the amount that you get that firm J gets out of it, and it's just a ratio. They split it evenly, the new capacity, and they split the cost. That's what. Okay, and then capacity is going to evolve. There's going to be, basically the old capacity plus the new capacity. The added capacity gives you the new total capacity, and same for the individual firm. Firms are making static choices, but we have to think about how capacity gets filled over time, or myopic choices. Okay, and the number of cables evolves as well, which is one of the variables we'll keep track of. And okay. So the firm gets profits. The firm J in period T gets profits, which are the sum over all the markets, revenue, cost, and shock. And they have some information set. Okay. Yeah. So and then we're gonna just imagine firm there's a Nash equilibrium. That'll be the firm side, and just tell you now we're headed towards a moment inequalities framework for estimating this part of the model. And so revenue is going to be so the revenue you get the firm J gets in market T from a given allocation of building, and these are all the states. That's kind of like what was already there. This is the stuff that gets built in period T. Is going to be basically just the quantity that gets transmitted over the network that they own times gamma. And gamma is like a per unit. You think of it like per unit profit per like megabyte that's being traversed, and that Q is just the total demand in the market times the share of the market that they own. This is the share of capacity that they own in that market. And gamma is the coefficient we're going to want to estimate here. So gamma is this kind of per unit thing. So we'll have a model of quantity. We have a whole data set on quantity. We can predict quantity, but the kind of profit from it is what we're going to want to estimate. And just to kind of tell you where, I'm going to go back to the slide now. We observe costs. So we're going to think we observe costs, we observe quantity, and we think between the two, we can figure out what that gamma is. What is the profitability per unit that allows us to rationalize that data in this kind of moment inequalities frame. Yeah. Okay, so data flows. This part this took some thinking to try to figure out the right model of how data flows were going to work. So we'll imagine that each pair of countries C and K has a potential demand M bar. So you've got some total potential demand, and then how much of it gets transmitted depends on these two elements. This is like the gravity equation stuff, the x's. Okay, so something about your distance and your GDP and stuff like that goes here. And then this is the quality of your connectivity. How connected are you with cables? And I'm going to have a functional form for this that's coming up. And then there's some loss that happens because connectivity isn't high enough, or maybe people just don't search for data. So some is being lost. And this is going to allow that as connectivity gets better or as income gets higher, there'll be more data transmitted between these two countries. So just to kind of give you a sense, like here's like three regions: North America, Europe, and Sub-Saharan Africa. And these green lines are supposed to give you a sense of how connected they are. Okay, so this is like a really big cable between here, and there's like a tiny cable and a slightly bigger cable here. So when North America and Sub-Saharan Africa want to interact with each other, the data can go through the direct path or through the indirect path. And these two paths together are going to generate the quality of connectivity between, say, Africa and North America. So this is there's going to be these country pair characteristics that I described, and the quality, which I have all three of these cables are contributing to the quality. Those two together will generate the quantity transmitted that we see. Okay, then once we know how much is being transmitted between these countries, we have to know which path it's going on. And so we're going to imagine this decision is made by routers. So we have to have a model of how routers choose how much traffic goes on these different paths. And you can see I drew it so the router cares a lot about capacity. They put most of the traffic this way and only a little bit of traffic this way. But we're gonna have a really reduced form approximation to what routers do. But it's going to care about things like distance, the number of cables, and capacity. Okay, so here's the kind of formal statement of that. The data between two countries gets allocated across many potential paths. There's going to be this many paths between each country, and we're going to specify a reduced form process for how data gets allocated to paths. And since, as Victor stated, I like work in IO and I have only one tool that I have only one hammer, then everything looks like a nail. I use a logit form for this. Okay, so I'm going to specify like a quality of the path delta. Okay, and then there's going to be the share that the router allocates to the path will be this ratio that looks very familiar to everyone. Yeah. Okay. I presented this at like a computer science, like a telecom computer science conference, and I was trying to convince them this is a good way to think about how routers are. People there that like spend their life like working on routers and stuff like that. There's actually a funny part that they bopped at that I'll tell you about when we get there. So anyway, okay, so here's my delta. Here's the function for delta. It's going to have a constant term. And then it's going to depend on distance. It's going to depend on capacity on the path. That's like, now we have to look at capacity in all the markets. A path is a set of markets that connect two countries. And we're going to have a measure of total capacity on the path, which is just actually going to be the minimum of the capacity on any of the markets in the path. So we're imagining like the lowest capacity market has some kind of constraint on how much can be transmitted. And then we'll also let it depend on the number of cables, and that's because this is like our measure of competition. If there's a lot of competition on the path, there'll be lower prices or better connectivity, or maybe the firms just care about redundancy. That's what Kyo and Stick are working on. So that's all captured by this kind of number of cables on the path. And just to kind of warn you about where we're going, if this theta were 0, if distance didn't matter, then the right thing to do would be just build like one giant cable from every region we'd have a star framework. Like we would build everybody would build a giant cable to Europe, and that's how we would do our communication. And as distance gets more important, we want to fill in more of that network. Basically, that's kind of where this is going. So
as the number of cables gets added to, are the new cables any different in quality than the old cables, or are they basically all the same?
No, they're dramatically more capacity. It's incredible how fast they're growing. They're just huge. They are better in other technical ways, actually true. And so yeah, I'll just say I didn't, just maybe to build on your point, when I drew that cable, when I put up that cable accumulation, kind of capacities accumulating, I actually didn't put a depreciation term in there. In fact, there are cables getting decommissioned. They're 25 years old. They just, I mean, we do account for it in the way we calculate things, but it doesn't really make a difference because they're tiny relative to the new stuff that's coming in. Yeah, I'm not sure if that's where your question was headed, but that's, yeah. So the new cables are better. Okay, and so then now we can finally specify that quality term. You remember, I'm going to have the amount going between two countries depends on the x's, which are like the Grabby equation type characteristics, and the B, which is quality. And what's V going to be? It's going to be an inclusive value of over the quality of all the paths. So more paths give you increased your connectivity, and the quality of those paths increases your connectivity. This vector point, I love inclusive values for capturing things, and so here it is again. Okay, so then now we can kind of say how much of this data is going to get transmitted on each path between each country in period T, and it's the total amount that's transmitted between the country times the amount that's allocated to the path. That's so that's how it's going to work. And then once we have that, now we can start adding up to the stuff we observe. Now it's just about adding up. Now here's the total amount of data between two countries that goes in a market. Remember, we only observe market level data flows. That's what we need to get to. And then that's this thing here. This is the amount of data that goes in a market, and it's going, we're summing over every country in the world. How much data do they send through that market, potentially on a very indirect route. Okay, and then we're going to have method of moments to match this to that dependent variable that we observe in the data. And critically, I guess I just want to say again, this is the vector of all choices in the world by all the owners. If they build a cable in one market, it can kind of affect flows throughout the world because firms might choose, the routers might now choose to route in that direction. That means less is going in some other direction. And so there's all this kind of network externality type of, we'll stop. Okay, so now a couple slides on estimation. We have a reduced form error, actually, although the model, we think of it as a structural model, it's kind of reduced form error. I think of D star as the observed data minus the prediction. This is supposed to be the same as this. Now we're taking out these two terms and putting in a theta, which is our parameters. Okay, and then we also have the first difference in this error term, so we're going to use both as our set of moments. We have a set of instruments for these. It's mostly about demographics and time. One concern you might have is that capacity is endogenous to usage. They're building capacity where they think usage is growing, and that would create an endogeneity problem for that capacity coefficient. So what do? We don't include capacity or number of cables in either of the Z matrices. We do pretty well without that, but what's even better for our results is we include lag values of capacity in only Z delta. So that's the idea is that when firms make their investment choice, they can't predict innovations in how demand is going to evolve, beyond the explanatory variables that we have, which includes the time frame. So that's kind of our identification assumption for fixing that endogeneity problem. Okay, and then on the investment side, we have kind of a moment inequality. I sort of mentioned we observe cost. This prediction of demand, we can say, like, with investment and without investment, what would this demand be? And then we can see how much capacity each firm would own. And then we're trying to back out what this gamma is, how much money are they making? We'll let this gamma vary to some extent. Moment inequalities can't have too many parameters, but we'll try to estimate it separately across some heterogeneous. We'll distinguish between the content providers and the carriers, and we'll let it change over time as well, which turns out to be really important. There's this structural error floating around here. For that, we use a first differences approach that's similar, based on Pecos Quarter-Ichiho. We difference across similar investors and non-investors in the same market. That allows you to take out the new, and we're using that as our main result in this version of the paper. We'll do it both with and without this first differencing. And then, okay, I'm going to just talk for 1 minute about dynamics. So I'm going to say a static model, which I feel sort of sheepish about at the Dynamic Structural Econometrics conference. Here's our attempt to do dynamics. And I'll just say, what is the problem with doing dynamics? In these moment inequality models, when we think about, deviating, let's say a firm changes from investing to non-investing, that non-investment is going to affect all their rivals, what all their rivals do downstream. And then you have to sort of predict that out into these future periods. And that's very hard to do. Maybe you use BBL or something like that, or some kind of forward simulation to figure out what's going to happen. And I'll just say, we never tried that. from day one, when we kind of saw the number of observations we had, we just thought, okay, these like two-step methods, we can't use them. We need like more of a full solution type method. I don't think anyone has actually done that in a paper, like used dynamics in a moment equality setup and putting aside PBL itself, which is not really moment equality. But okay, I'm gonna go on a tangent, but anyway, I don't think anyone has like used kind of a Pecos-Porter type moment framework in a dynamic model. I guess it could be done, but I think it's very challenging. So instead, we're going to make really strong assumptions. So this is, here I kind of state the problem. So here's our assumption. We're going to assume firms have foresight and perfect commitment. They assume they have full commitment. Thus, they're playing a Nash equilibrium. We can think of them as playing a Nash equilibrium, and the advantage of this. So instead of using Markov perfect equilibrium or subgame perfect equilibrium, we're thinking of a Nash equilibrium. So you can sort of think in period one, they make all their choices for every period, and we can think of deviations as just, in period three, I change what I do, but none of the other rivals are going to change their behavior. I still need to do dynamics in the sense I'm going to sum up the effects over time of what all the effect of this change on profits is, but it means that I can still use these kind of single deviation moment inequalities, holding the rivals as constant, because the rivals don't adjust these deviations in a Nash equilibrium and just kind of sum profits over the years. Let me just defend the assumption for a minute. Just want to say you need landing rights to do these tables, and you get them years in advance. And so the firm, these are kind of multi-year projects. Of course, the full commitment, full information assumption is surely wrong at some kind of length of period, but we feel like maybe it's more defensible in this framework, in this context than it is in other contexts. And so, in terms of implementation, we don't actually want to think like in our whole 20-year data set that kind of have a full commitment choice. So we break up the data set into 3 time periods. It's like 3 groups of years. And with each one of, and we're going to estimate separately for each time period, and which we were doing anyway when we in the static model. Okay, and then firms make their choice. They make all their choices you can think of the first year. Assume the states stay the same after the last year. They kind of just go on forever at whatever states are arrived at the last year of the period, and then estimate this kind of single deviation moment inequality. All right, so that's our attempt at kind of trying to handle this in a dynamic model, trying to handle a dynamic version of the model, which we've often received questions about. Okay, so finally I can show you some data. Here's used bandwidth over time. It's really growing, it's really going up fast. And just keep in mind, the whole network is optimized not to use these tables. Like Netflix, if they get a popular movie, they're going to cache it locally as much as they can. They're not going to just keep sending it over the cables because the cables cost money. YouTube, they're going to cache locally. The whole system is really putting their thumb on the scale not to use the cables, but it's still growing like crazy. And that's all driven by real-time communication, financial data. AI has a lot of kind of low latency and real-time demands, and that's what's driving this up over time. In 2020, I mean, we're just now we just went back to the company and bought more data, so it keeps growing like this very fast. This blue line is the number of new cables. There's kind of a dip in 2007. Like around basically after the dot-com boom, there's like a real dip in building of cables. You can see in capacity it really drops to almost nothing in after kind of the dot-com bubble. I said dot-com boom or dot-com bubble or dot-com crash, which is like 2001. Then things start to pick up, and then things really kind of lift off. You can see the number of cables is growing, the capacity is the red line, that's really growing. So it's and this is going to create those 3 time periods that we described, this kind of like very high period, this middle period, and this kind of early period up to 2009. One slide on kind of content providers. So basically, this is we have 4 content providers. It's Meta, Amazon, Google, and Microsoft. No investment in our data for 2009, really minimal investment up to here, and then just massive investment. This is 45% of world capacity during this period has one of these firms involved. Typically, when they're involved, they're the leading investor in the cable. In some cases, the first time we're seeing monopoly, like a single firm owning the cable. And then for this kind of Europe to North America, where you can see almost 80%, 75% of capacity is involved with these content providers. So they're really dramatic change. Here's our demand results. It kind of split up into this. This is the kind of gravity equation part. Strangely, for a gravity equation, we don't have distance, which you sort of might think belongs in a gravity equation. We do have market fixed effects, so that should pick up the distance between markets. And then this is the cable. You can see, GDP is positive, population is negative, but less than GDP. So GDP per capita makes things go up. Increases in GDP per capita would increase demand. And then this is the cable variable. And you see path length is very negative, a pretty big negative coefficient, and potential capacity is quite positive. And more number of cables, which you think of as like a measure of competition or duplicative or kind of redundancy, also increases demand on the path. Some kind of converting this to real values, but I'll skip that. We have another paper where we kind of do more specifications. We try other common language. GDPR is negative, as for Europeans that are thinking about it, because you have under the GDPR you have to keep your data in Europe, and so that's going to reduce demand. I'm not sure it's significant. I'm trying to remember where it comes in that paper, but anyway. But more or less, the router like shorter, higher capacity path. That's gonna try it. Okay, so now I'm gonna switch to the supply side. So someone was asking about how is capacity changing over time. So this is just a regression of capacity. This is just reduced form regression of capacity, log capacity on some explanatory variables, particularly time. And you can see it's like 14% per year, 15% per year. It's just massive growth over time in capacity. Meanwhile, cost is going down. This is like, we didn't even correct this for inflation because we don't know what inflation deflator to use for undersea cables. So we just left it in nominal terms. And you can see it's still declining 2.8% per year. Meanwhile, capacity, this is kind of interesting, length, if doubling the length practically leads to a double of the cost. Doubling capacity only increases the cost by 13 and 14%. So, you really get the sense that it's like laying the cable is the humongous cost, like getting out there with the ship and laying the cable. And you can sort of imagine if over time capacity is going up, that's going to raise the cost. There's a straight time effect, which is down. The overall effect is just slightly negative. It's practically zero. So cost basically is almost staying the same over time, even though capacity is going off the charts. Okay, here's our gammas. These are the kind of price per unit that the firm is getting. So we do it separately for the carriers and the content providers. Remember, there's no content provider in 2000 in the early period, so we just can't even estimate a parameter there. So the first thing is just focusing on the carriers is this incredible decline in gammas over time. Like, we just thought we made a mistake when we did this, but actually all the data we have on the price of internet transit over time declines at least this rate. And this is actually anything might be a tiny bit conservative here relative. I mean, just the price of transit is dropping rapidly and the quantity is expanding amazingly. So this actually looks surprisingly realistic, these numbers. And then you can see comparing the content providers, it's pretty similar here. If anything, they're a little bit lower in the gammas. And we think that reflects the fact that basically the content providers are making decisions that don't maximize quantity transmitted on the cable. They're really making money in adjacent markets. So they're kind of not driven by the profitability. In this transit market, they're driven by other markets. So we're getting that they kind of like aren't that responsive to the amount that's transmitted in the market. So we get, not in a way that we can conclude it's statistically significant, but if anything, it's slightly lower. Okay, so we have any robustness checks? 5 minutes. I'll skip my robustness checks. So here's so we start with this very low usage, This is kind of usage in 2020, the yellow line, and the blue line climbs up. And the question we ask is, what if you kind of could move the quality of the cable network to the 2020 level? What effect would that have on demand? And that's this kind of red line where X stays at the observed level for that year, and the quality goes up to 2020, and we can do the same verse thing, keep cable quality at the observed level for that year, and just move up all the demographic. So the question is, how much does demographics consider to contribute to growth relative to cable quality? I think everyone thinks demographics and time trends and things like that should matter. A lot of people use the internet a lot more than they used to, but you can see that the contribution of the cable network, at least as you get into the later years, where frankly our model fits better, is comparable. So like this is a sense in which cable investment seems to matter for the result. By 2013, the two have a comparable effect on kind of raising the quality of raising the amount of usage in the market. Okay, so now we're going to oh, this is, I don't know why this looks so weird, but now we're going to think about what would a planner want to do. The planner wants to build in all the red markets, which is actually kind of a mix of big and small markets, which is relative to an entrant that would find only 7 markets to be profitable, which is not that far off from what we see in the data. We're going to do a little bit on, we have a kind of a back of the envelope way of calculating consumer surplus, so that we can compare total surplus and consumer surplus, total surplus and entrant profit. If the market were perfectly efficient, these would be perfectly correlated. The red and the blue would be perfectly correlated. It would always be like the more entrant profit, the more total surplus would be generated. It's not that far off. The blue and the red are clearly correlated with each other, but there's some interesting views. For instance, here the blue is much lower. Here the blue is negative, so the entrant makes negative profit, even though there's positive social surplus. Here the entrant would probably pick this East Asian and North America route, where the social planner would pick this Europe to South America route. So there's some kind of interesting deviations here. One thing you don't see is evidence for business stealing. That is, there's no cases where the entrant kind of would do better than total surplus. That would be business stealing. And that's kind of the first clue. This is really going to be about the network, the network elements of this. And so it really varies across markets, I should say. Because I'm out of time, so I'll sort of skip ahead. But you can see, like in Europe, the entrant profit is up here, and a lot is being stole from the incumbent. In East Asia, Sub-Saharan Africa, almost nothing is being stolen from the incumbents. We kind of break out how all this surplus moves. So like East Asia, we see like very little business stealing, large out of market externalities, and we would need like subsidies to kind of get a de novo entrant to come in. Okay, so I'm going to stop. I have some more kind of slides I can show you, but I guess I'm out of time, and maybe I should take a question before the whole thing's over. So I'll just say we study investments in subsea internet cables, and we have this model. I guess I can let you all read it. I'll just say I think I'll finish with some like gloating. I think we feel kind of like when we started the project, it felt like talking about the equipment layer of the internet was not that interesting to people, and they really want to talk about Google and Amazon as kind of on the application layer and software and things like that. But it feels like now, to me, over the last couple of years, with all the discussion of AI and investment in data centers and infrastructure and now cables as well, like I think people are a lot more clued into the importance of the equipment layer and how it affects what we can do in the sort of application layer. So we feel like things like moved in our direction a tiny bit, and we're excited about that. As researchers, I don't know if it's good or bad for the world, but good for our research program. So thank you so much. Really a pleasure to be here.
And any questions from the audience? You mentioned briefly you went to California.
Oh, and a funny story, yeah.
That,
So, okay, I'll talk it. So I was showing the chart kind of like this one. And one of the computer science guys like, you economists with like organizing the whole world, it's just crazy. Like, what is this consumer surplus thing? Like, you know, and I have a formula somewhere here, but he definitely didn't want to see the formula. So I was like, well, it's like, you know, I understand it's sort of like a black box, but basically it's like more quantity is good. Like the more quantity gets transmitted on the internet is like good. So, you know, that's kind of what I'm thinking about, that consumers are happy when there's more quantity. He goes, even gambling? I'm like, you know, I'm an economist. I said, like, I'm an economist. I don't judge, you know. Like, he goes, even pornography, even child pornography. I was like, okay, you got me. Like, that sounds bad. My model doesn't capture it. My model would say that was good. I was like, okay, you got me. So anyway, that was my experience. That was one of my. Some great things came out of going to that conference, I should say. But that was a tough one. Thanks for the question.
Yes, we have time for one more.
It's good to go to dinner.
Yeah, if not, let's thank Mark again.
But before we do go to dinner, thanks, Mark. This conference has been incredibly well organized, and we really want to thank Glenn and Yaja and Jasmine for organizing it. The winter school, of course, is also perfectly organized. If we can get into a clap later on. But for now, let's thank our organizers and the team underneath them too. It's just like, wow, luxury premier first class service. I'll never see it again, but I'm really glad I got it over these last 2 days. So let's thank our organizers.
Okay. Well, thank you, Bob, for your kind words. Yeah, I really was more or less organizing everything, but really, if it wasn't for Jasmine and Najah, this wouldn't happen, okay? I get very frustrated when things don't work, but they keep calm and look for second best all the time. So thank you. And thank you to all the HKU helpers, the PhD students who help you shepherd you around, and they are the heroes here. And also our team, our staff, Darren and Daisy, that get a lot of little letters on time. And so a big round of applause for them as well. Thank you to Mark and our other 3 wonderful keynote speakers. And also to the DSE again, and to the Econometrics Society for trusting us for this event. The DSE school continues for 2 more days, but the conference ends here. 2 advertisements. I think the DSE is having another DSE event soon in next summer. Where is it? Michigan? Michigan. So if you want more, I think it's based more related to finance, but if you're interested, look for those announcements. And one for HKU. We are organizing the Asian China meetings of the Econometrics Society in June. So if you want to come to Hong Kong again, please look up for those call for papers. And that's it. Thank you, and I'll see you soon.